is a transformation. This one actually is a translation. What do I mean when I say translation instead of transformation? It's just going to move the function. It's not going to stretch it or compress it, right? So I want you to show me the transformation of the mother function and then give me the new table, right? Yes? Good. So when I complete the square here, I group my x terms in the parenthesis and leave the constant outside the parenthesis. I want to make sure the leading coefficient is not anything but 1, positive 1. In this particular case, it is positive 1, so I don't have to do anything. If it wasn't positive 1, I have to factor it out. So now I ask, what is the coefficient of x with the sign? What's the coefficient of x with the sign? What's the coefficient of x? 1. Positive 1. Make sure you take the sign with it, right? I find half of that. That's my k value. That's 1/2. And I square half of k, right? So I get 1/4. Everybody with me? I'm going to add 1/4 on the outside and subtract 1/4 on the inside. Now, if I simplify everything, if I get rid of my parentheses, I should still have the same original function. Of course, in this case, the 1/4 and the minus 1/4 just cancel, and it's obviously the same. This will always turn into x plus half of k, quantity squared, and then what do I have, 3/4? Yes? You can always double check this. I don't think you should have to. You're in pre-calculus. You're not in algebra anymore. Yep. One minus 1/4. Yeah. Usually I do my arithmetic in my head, but if you don't see it, tell me, right? I got a common denominator of 4, right? 4/4 minus 1/4 is 3/4, right? So there it is. What's happening to my table? What's going to happen to my table in this case? What am I doing to the inside value? What am I doing on the inside? Adding 0.25 or 1/4, right? But I have to think inversely for the inside. So all my x's are going to move by minus 1/4, right? So what? Minus 1.75 minus 0.75 minus 0.75. Oops, sorry. What did I do wrong? Oh, 1/2. Sorry. It's 0.5, right? 0.5, right? So minus 2.5 minus 1.5 minus 0.5. Positive 0.5 and positive 1.5, yes. All my x's move left by 1/2, right? We agree? And then where do my y's move? Plus 0.75, right? And of course I want to graph both of them on Desmos, maybe do the table on Desmos, right? It's just what we learned, and that is I'm looking at what's happening to my inside values, what's happening to the outside values. We okay? Ben, you asked for that? Yeah, and is that okay? It's helpful? Anything else? Anything else? Nothing else. So I always give the quiz at the end of class. 1, in case you're running late. 2, if you really know what you're doing, you'll be out of here in 5 minutes. So you just leave after you're done with the quiz. I'll have solutions for you Monday. I said the test would be next Wednesday, but I'm going to move it one more. So we'll just have another quiz next Wednesday. Quiz next Wednesday, and then the test the Wednesday after. So test on the second Wednesday in October, okay, instead of the first Wednesday. All right, I can move on. Yes? Nice. So we're talking about chapter 4 today. We have three sections on polynomials, and we have 2 sections on rational functions. So 3 sections on polynomial functions, 2 sections on rational functions. The idea is that we get used to all of these different types of functions so that in calculus, when I say here's the function, you're going to know its domain. You're going to know how to find its intercepts. You're going to know where it's increasing or decreasing. You're going to know when it's positive or negative, right? So every type of function we're doing this with. So there's a lot of repeat here. Like as we learn polynomial functions, I may say, hey, let's find a difference quotient for a polynomial function, right? As we do a rational function, I'll say, let's do a difference quotient. So we're going to be repeating themes all semester long with different types of functions. Again, when I give you a function and you don't know what it looks like, graph it, okay? Graph it. Even if you were taking this at University of Maryland, College Park, they don't allow you to use calculators or graphing tools. But when you're practicing, you're still going to do it. I need you to have the visual, the geometry of things, and the algebra. Okay, I need you to have both for when you move into calculus. So, I guess what we have to talk about first is a polynomial, right? What is a polynomial? Ask. So we'll call it P of X, right? It's just polynomial, right? F of X, G of X, P of X, anything I want. So P of X is going to be A sub 0, X to the 0, plus A sub 1, X to the 1, plus A sub 2, X to the 2, plus dot, 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 all the way up to A sub n, X to the n, is an nth degree polynomial so if I end at x cubed, it's a 3rd degree polynomial, right? Does that make sense? If I end at x to the 4th, it's a 4th degree polynomial. And with each a sub I belonging to the real numbers. So there's a piece of this class that talks about complex numbers. I don't know how many of you know about complex numbers, but we're only going to deal with real numbers, okay? So there's a section, 4.4, which deals with complex roots. We're skipping it. There's a section on complex variables inside of functions in chapter 9. We are skipping it, okay? Why? Because calculus doesn't have any complex numbers in it. And so I don't know if you remember learning this, but I could have the real axis here and the I-axis here. And so if I had something like this, this would be 1 plus 2i. That particular point is 1 plus 2i. I being what? Anybody remember? Square root of what? -1, yeah. So this is called an imaginary number. I mean, no one ever says, hand me that 2, right? So kind of all numbers are imaginary in the sense of we just thought of them, okay? But these particular numbers are called complex numbers, as it involves this strange number of square root of -1. If I square both sides here, what do I get? I get I squared equals -1. Remember, a square will cancel a square root. So why is this bothersome to anybody? How could you square something and get a negative out of it, right? Because a negative times a negative is a positive. A positive times a positive is a positive. Anytime you square something, you get a positive. Unless we're in this imaginary plane, we are not talking about this at all. But when you hear me say this root is complex or this 0 is complex, no, it's in this other world of numbers. Okay. So again, for us, we're only using real numbers. So what about this notation bothers anybody? Anything here I've written that bothers anyone? Well, how about this a sub I? A sub I, right? Subscript I. It's a coefficient, right? So the first, the 0, the initial coefficient, the next coefficient, the next coefficient. So I'm saying all of those coefficients are real numbers. They can't be complex numbers. And this is my polynomial, right? And what the hell? So that's what this says, right? All coefficients are or belong to, right? The real numbers. And I like to think of the real numbers just as like in second grade, you had a number line on your desk. You remember that? Any number on that number line is a real number. Like 1 is on that number line. 3.14 is on that number line. Pi is on that number line. These are all real numbers, right? 1/17, -7, right? You with me? So we want to talk about worst case scenarios with polynomials. So if I look at y equals 3, technically it's a polynomial, right? It's x to what power? Look at my polynomial. What's that very first term? X to the what power? X to the 0 power, which is 1. We have to be careful of that. Sometimes 0 to the 0 is very troublesome, but we're really going to consider x to the 0 to be 1. But I want to go to y equals x plus 3. What does that look like? So the horizontal line is weird. It's a weird polynomial. So most of the time we'll talk about it in the same kind of thing, but I consider it a polynomial. It's boring as hell. But x, so there's no x in y equals 3, right? So there are no roots. And it's weird when what if it was the x y equals 0, then it's the x-axis, and there's an infinite number of x-axis. But this one, how many times is it the x-axis? Once. Right? Once. That's the one. Yep. So it hits the x-axis once. So there's one root. How many times if I'm driving on that road am I turning my wheel? I'm driving on that road. Am I turning my wheel at all? No. So there's 0 turning points. One route, 0 turning points. One route, 0, x-intercept, all the same thing, right? No turning points. Next one. Y equals ax squared plus bx plus c. What does it look like? What shape? The official name is a parabola, but what does it look like? A smiley face or a frowny face, right? When A is positive, right? Jorge, did you say that? Yeah, like a U. Yes, like a U or upside down U, right? So worst case scenario, it could be here. It could be here. It could be here. Could be anywhere really, but notice how many zeros it has. How many zeros? How many times does this one hit the x-axis? How many times does this one hit the x-axis? How many times does this one hit the x-axis? So up to 2 roots. How many times do I turn my steering wheel when I'm driving on that road? And remember, this is the flat. I'm looking flat onto the road, onto the map. It's not a hill. I'm not driving this way. Right? I'm driving on the road. Right? How many times am I turning my wheel? 1 time. Yeah. So we kind of are seeing a pattern here, right? This is an x to the 1. This is an x squared, right? Let's go to x cubed. So y equals ax cubed plus bx squared plus cx plus d. I could do this, right? I could do something like this. So I'm just showing you worst case scenario. And it's kind of fun to play around with this. Yeah, exactly. How many roots do you see? More than 2. 3. The red one, you see the x-axis 3 times. So I have up to 3 roots. So again, it's an x cube function. The cube is telling me how many roots there could be. And 3 minus 1, so the power minus 1, how many turns? Imagine yourself driving on the red road or the black road. I'm turning to the right to start, and then turning to the left, 2 turns. So it's the power minus 1 for the number of turns I could have. It's kind of fun to play with this on Desmos if you can open it for me. It's fun to play around with this a little bit. In Desmos, nice, easy to make little animations. So I'm going to say y equals ax cubed. I use the up arrow for cube. Up arrow cube. Right arrow plus bx squared plus cx plus d. And I want to make them all sliders. And I'm going to animate them all. Just get to the square or the cube, use the caret up arrow. Buffy, you got a mask? We need a mask on every day, I'm sorry. Until they tell us otherwise. Ben, yes? I'm thinking October 1st is going to be the mask will be optional. So look at this thing. I'm just letting these things coexist go wherever they want. It's right now one root, two roots, one root again, right? See? So we're just thinking about what are the possibilities. So I'm just going to put some values here. Here's one I want right there. There's three roots, right? Yes. 3 times the xx. So, and we're going to want to find those roots. That's our whole goal in this section, is to be able to find the roots of any polynomial. As long as they're real. If they're not real, then we won't bother. In fact, you'll learn the fundamental theorem of algebra. The fundamental theorem of algebra says there in an nth degree polynomial there are exactly n roots with multiplicity. So in this one, how many roots can you see? 1, which means there must be 2 others. But guess what kind of roots they are? In this case. But it's imaginary. So the fundamental theorem of algebra says every polynomial can be factored to n roots. That's polynomial, right? X power, it should be n roots. Some of them might be complex. So the imaginary numbers because they don't have their axis. Exactly. They're hitting the imaginary axis. So I think we can do the quick summary here for worst case. I spell worst. Yeah, I know. Worst case summary. Right? Every nth power polynomial has at most n roots. I'll say real roots because that's all we care about. And has n minus 1 terms. So definitely want you reading the textbook, okay? I'll go back to that in a second if you need me to. Right, up to n roots, n minus 1 terms. Yes? Yeah? N real roots and n minus 1 terms. So I definitely want you reading the book. I speak differently than the book on purpose because I want you to just be able to talk as you would normally talk to somebody, or even tell a family member what's going on with a polynomial kind of thing without being super nerdy. The textbook will get a little bit nerdy, but we're reading chapter 4. 4.1, 4.2, 4.3 is where we're focused on right now. Come on, book. Any day, book. It's trying to open. There we go. So if we go into chapter 4, into 4.1, right, there's their polynomial definition. They did it different than me, but that's fine. And so they'll simply ask, is this a polynomial or not? And then what's the mother function, right? Can you see it okay? Is this a polynomial? Yeah. Then what's the mother function? 5x cubed. The one that's leading, piece that's really in control. The one that's dominating the other one, right? Is this a polynomial? Yep, it is. What's the power? Yeah, fourth power, and the mother function is minus 3x to the fourth. So I want to take the coefficient from everything. Is this a polynomial? No. That's x to a 1/2 power. I want my powers to be integers, right? 0, 1, 2, 3. Yeah. Polynomial? No, that's a rational function, like a fraction ratio. Say again? So they have to be whole numbers to be considered a polynomial. I have to have some number times x to the 0 plus some number times x to the 1 plus some number times x squared plus some number times x cubed, right, up to wherever I want. Yep. So we'll talk a lot about this in calculus, but polynomials are like roller coasters, right? No loops, no gaps, no holes in it, no real sharp points that would probably hurt a lot on a roller coaster, right? So nice smooth curves. We really want to talk about those power functions in that we're just talking about the mother functions. So it's going to be a times x to some n is a power function. And we already know what a does, right? What does a do? What does that coefficient do to the graph? Stretch or compress, right? In the y direction, right? And so we want to look at these power functions. I'll try and do a couple of them. Y equals x. Y equals x squared. Y equals x cubed. Y equals x to the fourth. They start to look like each other after a while. But notice, what about the odd ones? What about x to the 1 and x cubed? Where do the odd ones start? On the left, down at negative infinity. And where do they end? Positive. Where do the even ones start? Right, you see x squared and x to the fourth, they both look like that parabola. They start at positive infinity and end in positive. So all those power functions are mother functions, right, that we talked about. And of course, like if I say y equals x squared and y equals x squared plus x plus 1, the mother is y equals x squared. Eventually, we become our parents. If you haven't, by the time you're 30, you're going to go, oh my God, this is what my father does. Right? Eating breakfast, talking about what's for lunch. Eating lunch, talking about what's for dinner. Right? That's my father. But eventually, this guy looks just like this. We become our parents. Power functions are mother functions, yeah. So on Desmos, I want to just look at those two functions, and I want to recognize that in the long run, they are the same. So what do I have? Y equals x squared, and y equals x squared plus x plus 1. It's hard to tell, but they're getting closer and closer together. And eventually, as I go higher and higher, right now I'm at 315, right? Think about it. If I put a billion into x, right? If I put a billion into x, billion squared, this one too. A billion squared plus a billion and one. If I have $1 billion squared, I certainly don't care about the $1. I probably don't even care about the other billion. Billion squared is a lot of money. So eventually, who cares about those other pieces? It's not quite doing the demo as much as I'd want it to do, but this will help. You see? They start to look exactly the same in the long run, but in the short run, look at this. At the origin, look at. Are they the same? No. So they start out different, but they eventually become the same exact line. Right? When x goes to infinity or x goes to negative infinity. Yeah. Yes. It's so the turning happens in the short run. The turning's going to happen close to the beginning, to the origin, and the other stuff is just what happens when you plug in a really, really large number. Right? You're asking me about the end behavior, what it looks like at the very end, and then worst case scenario. Worst case scenario. So you said x to the 4, right? Yep. So let me just put one in real quick. Ax to the 4th plus bx cubed plus cx squared plus dx plus e. And I'm going to make these all sliders. I don't know why I lost my e value, but that's okay. So this one looks like 2 turns, right? So at most 3 turns is what I should have. Let me see if I can get one. This one's 3 turns. Do you see the 3 turns here? So I'm looking down onto the road. I'm driving on this road. I'm turning my wheel to the left, right? Then I'm turning my wheel back to the right. You see it back to the right a little bit, and then back to the left. I'll never get more than n minus 1 turn done. Oh, sorry. And it's a little bit weird. I mean, you're kind of trusting me on this. I don't know why I can't get slider E. But I'll stop right right there, stop. This is a good one, right? This is, I mean, if you were watching, you would see this is the most turns I could possibly have. But again, this part turning to the left, turning to the right, turning back to the left. I'll never get more. This one has how many roots? 1, 2, 3, and that third one is repeated twice. There's really 4 roots. I'll always get 4 roots for that fourth power. So that's burning them? Yeah. Yeah, I'm pretending it is. Yeah. So it's actually happening twice. So for example, right? F of x is equal to x minus 2 times x plus 1 times x plus 3 squared. So if I FOILed this all out, which would be horrible, right? 4-letter F word, FOIL, right? Horrible. I would have an x to the 4th power. You see it? This one's going to give me an x squared, right? That's another x, that's another x. But and what are the roots? I got a root of 2. You agree? What's going to make it 0? 2. That's got a multiplicity of 1. A negative 1 has a multiplicity of 1. And a negative 3 has a multiplicity of 2. And so what I'm talking about is, right, I certainly could write this like this, right? X minus 2, x plus 1, x plus 3 times another x plus 3. So I'm just saying, how many times is that factor repeated, right? Yeah. So multiplicities, okay? So what's strange is that odd, even multiplicities bounce. This is a Robert term. Odd multiplicities go through. Even multiplicities bounce, odd will go through, and this will make a little bit more sense in a second, okay? So, but let me put that one on Desmos. And I'll go back to this in a second. Just let me put this one on Desmos. So I had f of x or y, right? Sometimes we want to use one over the other. You'll see when. What did I have? I had x minus 2, right? I had x plus 1. And I had x plus 3 raised to the 2nd power. So you can see at 2, it goes through the axis. It's a multiplicity of 1. At 1, it goes through the axis. A minus 1, so again, a multiplicity of 1. But at 2, or sorry, 3 here, it bounces off the axis. Right, it'll like hit it and then bounce back off. So the point is not on the x-axis. That's right, it's not a root. It's not a 0. Right? It's got to be hitting the x-axis to be a 0. If I negate this, again, it's still got that x plus 3 repeated. It bounces again, right? You see it doesn't go through. If there's an odd multiplicity of a higher level, like I'll make this plus 1 to the 3rd power. Again, it's an odd multiplicity again, right? At minus 1, it goes through the axis, but it looks like xt. When it's an odd multiplicity of level 1, it looks like a straight line. when it goes through it as an x cubed, it looks like a cubic function. When it bounces power 2, it looks like a quadratic. It looks like the frowny face, the upside down U, the smiley face. So we're just looking for these things, because what we're going to be doing is we're going to get a polynomial, and I'm going to say to you, find me all the roots. How does it behave in the long run? How many, right? So just like little things like that. So talking about even powers, odd powers, right? Yeah. Transformations of polynomials, yes. So like this one, what's the mother function of this transformation? What x to what power? X to 4. Right, with me? I've got an x minus 1 to the fourth power. So it's x minus 1 times x minus 1 times x minus 1 times x minus 1. There's going to be an x to the fourth power. And then what does it? So it takes the x to the fourth power, right, and moves it to the right one. There's my x to the fourth. There's moving to the right one. And then what's it do to it? It compresses it by 1/2. On the outside is a direct, right? So we're going to be trying to factor things. Let me get to a problem, right? So here's our first type of problem, is I'm going to give you the zeros, and I want you to find the polynomial. So let me jump to a problem here in the book. Sorry. Number 43. I want a polynomial with these 3 zeros and degree 3, right? When they don't give me an option, we'll say that the leading coefficient is 1. Instead of it, like it's saying, let's do any leading coefficient here. So number 43, I want a 0, I want 3 zeros. I want it to be of 3rd degree, right? And I want the leading value to be 1. So this is 4.1. Yep. And I just want to take a picture of it real quick. Number 43. So our model is going to be f of x equals a times x minus z sub 1 times x minus z sub 2 times dot dot dot. And z sub 1 is the first 0. Z sub 2 is the second 0. Z sub 3 is the third 0. Yes, you with me? That's my model. So I'm going to have zeros of -1, +1, 3, and n is 3. So I need 3 zeros, right? So and a is 1. For us, a will always be 1 unless they tell us differently. Okay? So I've got now f of x, my model now is 1 times x minus z1, x minus z2, x minus z3. Right? I'm taking my general model and turning it into the model for my problem. I know the value of a. I know there's 3 zeros. So now what do we get? We get x minus a -1, x minus 1 and x minus 3. The book might ask us to expand it, right? So I'm foiling here, right? And now I'm foiling here, yes? So I get x cubed minus 3x squared minus x plus 3. No problem. It gave it to me. It gave it to me. I'm saying in general, just let A be 1 unless they tell me differently. It just makes it easier because the book answer will have A as 1. Now, when I'm doing these things, I want to be checking my work on Desmos. Is everybody okay with the distributing here? So I really like to make sure that I'm doing things correctly, especially if I'm doing a quiz or a test. I want to make sure that I got things right. So what I'm going to do is I'm going to go to Desmos. Well, wait if you're still copying. So I want to go to Desmos. And I'm going to graph these two functions, right? My original was y equals, what was it, x plus 1? X minus 1 and x minus 3. Yep. So there's that function. Again, 3 roots, 2 terms, right? That's the worst case scenario. And graph my expanded one, right? So I had what, x cubed minus 3x squared minus x plus 3. And what I'm noticing here, if I turn off the green, if I just click off the color, you can see my two polynomials are exactly the same. So when you're doing things and you create a polynomial, by the way, the first one's called factored form, obviously. The second one's called standard form, right? When you see ax squared plus bx plus c, we call that standard form. When you get it factored, it's obviously called factored form, right? So getting from line 1 here in Desmos to line 2, easy. What we are going to learn to do by 4.3, 4.1, 4.2, starting with this one, getting it back. All right, let's take a little break. Let's come back at 3:05. In my zeros, put in the point, and then figure out A. So right away, I have f of x equals A times, my first zero is negative 2. That gives me a factor of x plus 2. Does that make sense? It's x minus a negative 2, so x plus 2, right? My second factor, my zero is x minus 0, so I could just call it x, of course, right? And then x minus 2. This okay? Yep, so I have a times x plus 2 times x minus 2. I could expand now. I certainly could expand now out to standard notation, right? Or I could find a first. So this is a times x squared minus 4, right? Hopefully that foiling those things out are pretty quick for you. It doesn't matter. I'm saying it really doesn't matter when I put this value in. It should always give me the same value of a. Let me stop here and put in my point. So I have to put in negative 4. And I should get out 16. I put in the -4 for every x, and what I should get out is the y value of 16. So I get -4a. Help me. What's -4 squared? 16. So I get -4a times 12 is 16. So -48a is 16. So a is 16 over -48, which is what, -1/3? Is that true? Yeah. Yeah. So I've given you that I have 3 zeros, multiplicities of 1, understood unless they tell me a different multiplicity, and they gave me 1 point on the graph, right? Yeah, so I put in x, so that first 0 went in as an x minus a -2, which of course is x plus 2, right? Yeah. Yeah, I just started, I noticed that, I could rewrite this one very easy, right? Yeah. And then I see that I want to eventually get my standard form, right? So in this particular case, I started expanding. So, exactly. So my final answer here is -1/3 x times x squared minus 4. That's what I had gotten, right? I probably want to go further. That's -1/3 times what? X cubed minus 4x. So final -1/3 x cubed plus 4/3 x. I'm not doing anything but multiplying, right? I'm distributing the x in, then distributing the 1/3 in, the -1/3 in. So this is my standard form. My factored form was what? X times x minus 2 times x plus 2. The point I had was, what's the matter, CD?
So I'm stuck at the part where you said x plus 2 and x equals 18 and it becomes like 4.
Oh, sorry, because I made a mistake. I was thinking about the point. So are you okay here is my first question. Are you okay there?
Yeah.
Good. So at that point, I could figure out A. At any point, I can figure out A once I get my zeros in. Do that when you want. I don't care. But I want at the end, I want the factored form and I want the standard form. Yes. Good. So watch what I want to do now. I want to go to Desmos. And when I go to Desmos, you go to Desmos. I want to put in my factored form. So I got equals -1/3 times an x times an x minus 2 times an x plus 2. And I want to see if my point falls on that graph. And my point was -4, 16, right? There it is. So it points on the graph. So I know it's right. Yes, you with me? I also want to put in my standard form to make sure I did all my algebra correctly. Okay? So I want to put in my standard form. So I got y equals -1/3 x to the third, right? Plus 4/3, oops, 4/3, I forget already, 4/3 x. And what I'm trying to see is, are my graphs matching, right? Is my red graph and my purple graph, are they the same graph? And that's when I know I got it. Yeah, question. Say again? Both. I want both. I want the factored form. I want the standard form. Yes. So again, right, I was given the zeros, given a point. So I knew what model to use, right? I know what model to use. Yes, that makes sense? This is the model, always that leading coefficient and always the number of zeros I have, right? So I plug in the zeros, and I just said, hey, well, this is so easy to expand, let me just do that, right? The more I expand, probably the easier it is to find A. Maybe not, but doesn't matter. We found A. You can find A at any time. And then at the end, I want to be able to write those two forms and the point and check them on Desmos. John, you got a mask? Sorry. I hate asking you have to put a mask on, but it's not my rule, right? So, but I do believe, and I think I told you this, I think mask will be optional in October and on. Until, of course, everyone gets sick again. Right. Okay, okay, let's do another one, yeah? You know, you have nephews or nieces or even little brothers and sisters, and they want to play a game, and what are you going to be, miserable and play the game? Are you gonna do that? Why bother doing it, right? So again, here we're playing a game. You could be in misery and hate it and just, oh God, or you know, maybe change your major if you don't want to do this math. And believe me, you got some tough stuff coming in Calc 2 and Diffie-Qs if you're engineers. It's tough. So try and fake it till you make it. Pretend you love it. Yeah. Fake it till you make it. Let's do another problem.
Similar to this one, right?
Say again?
Isn't the problem similar?
Yeah, yes, of course, yeah. So we're looking at zeros and multiplicities. CD, I'll do another one similar to that in a second, but this is another kind of topic. We're trying to ask, what are the zeros? What are the multiplicities? Does the graph go through or touch or bounce, like I said? The number of turning points and the end behavior. What does it look like? What's the mother function, right? So let's do 63 here. So this is 4.1, number 63. And it's kind of nice. You can just think about everything. When I give you a polynomial, right? You think about everything you could possibly do to it, right? And so this one is already in factored form, right? You agree with me? Do you know what it looks like? Anybody see the mother function right away? What's the mother here? Yeah, x to the fifth. Nice. Right? So in the long run, it's going to look like an x to the fifth curve, whether x is going to positive infinity or negative infinity, right? What are the zeros and the multiplicities? Well, there's two zeros. There's a 5 and there's a -4. Do you agree? And the multiplicity of the 5 is 3. So that's going to go through the axis like a y equals x cubed function. And at -4, it's repeated twice. So that's going to bounce like an x squared function. Say again?
So when doing this type of problem, it doesn't matter which one's a zero and which one's a multiple.
Yeah, so the 0 comes from when does this, right? When I'm saying 0, I'm saying when does this thing equal 0? And the multiplicity is coming from that power. Yeah, nice. So let's look at the graph. So I had y equals x minus 5 to the power, so caret 3, right? And then what was it? I forget already. X plus 4 to the second. So really kind of horrible looking graph. What I really like to do is when I start a new graph, I like to start a new Desmos page because it always goes back to a nice looking window. If I like stretch it out, I can get it to a pretty bad place. So I'm going here. That's still pretty bad, but it's okay. So do we know what x to the 5th looks like? Yes, right? X to the 5th is just looks like x cubed. Okay? X to the 5th looks like x cubed. It looks like x to the 7th. Starts low, ends high, right? So I already got my zeros at -4 and 1, 2, 3, 4, 5. And I know it bounces at -4. So it's got to come up and bounce, right? And then it's got to go through at 5. So I can get it. So it's hard to see this graph here, but you still see the same thing, right? It starts low, like this. Starts low, comes up to 7, right? And then comes up to 5 and goes through like a cube, right? So when I'm doing stuff by hand, I just want you to be able to show me that it would bounce or go through, right? And it looks like the model pump. Right? Starts low, comes up, and high. And then what happens in the middle, we're going to let the zeros tell us. This one is horrible to expand. I typically won't, sorry, x minus 5, right? I typically won't ask you to expand something like this. I mean, but I guess you could, right? I'll say this: if the book tells you to expand it, right? I don't think it will on this because I got a lot more to do, and I'm already bored. But on the first one, I did definitely want to expand it and give me standard form.
So before that,
Exactly. I foiled 2 of these to get this guy, and these 2 gave me this guy, and then I still have another x minus 5 to deal with. But it's boring me. I don't want it to keep going. All right, let's do another. So I think I gave you 75 to do. Let's do 70. And then we'll take our quiz. We'll take it a little early. So this is like, CD, this is like the one we had done previously. So I can already see that I've got a root where, a 0 where, and number 70. Where's my root? Yeah, -1, and it's repeated how many times? It bounces, right? So it's either repeated twice or 4 times or 6 times or 8. They want us to take the minimum. So twice, because it bounces. At -1, the curve hits the axis and goes back up. Do you see it? That's a multiplicity of an even power. The book is saying take the lowest multiplicity you can. At +2, it bounces again, right? Yes?
Yeah.
So I have again a multiplicity of 2 there. And what point do I go through? Nope. What non-zero point do you see on the curve? 0, 1. X is 0, y is 1. Yes? You with me? So we're instead of us getting all the zeros from the book, it's saying give us the graph and we should be able to figure those things out. So again, here it is, 4.1, number 70.
So it's a multiplicity of 2 because it goes up.
Exactly, because it bounces, yeah. So there's our graph. We know we have a 0 and a multiplicity, right? We have a 0 at -1 with a multiplicity of 2. Because it bounces, yes, you with me? And we have a 0 at 2 with a multiplicity of 2. It could be a multiplicity of 4 or 6 or 8, but it's telling us take the minimum. So meaning if it bounces, take it as multiplicity of 2. If it goes through, multiplicity of 1.
This chapter we're not going to do in class.
Say again?
This chapter we're not going to do in class.
Well, right, so our x is independent, right? So the y kind of follows. The y kind of just gets what it gets. Yeah, so the point we have is 0, 1. So what's our model? F of x is a times x minus z1 squared times x minus z2 quantity squared, right? Because I had 2 multiplicities of 2, right? We okay here? When I put in the -1, I get x plus 1 with a multiplicity of 2. And when I put in the 2, I get an x minus 2 with a multiplicity of 2. At this point, I want to put in my my point and figure out the value of a. So I know if I put in x is 0, I'm supposed to get 1 out. If I put in x's, I'm supposed to get a 1 out for my y. So it looks like a is 1/4. We okay there? Nice. So I got my final version, not expanded, but let's just deal with this first. 1/4 x plus 1 quantity squared times x minus 2 quantity squared. Let's just put that in with our point 0, 1 and see what if we get a similar picture as the book, right? So going to Desmos, y equals 1/4 x plus 1 raised to the second power, oops, times x minus 2 raised to the second power. Boom. Look how cool Desmos is in terms of giving us information. What did it give us? It gave us the 0, right? See the points on the 0? It gave us the x-intercept, y-intercept, and it gave you what else? See what else? What are the points? A high point, a maximum. Well, it's called a local max. It's one of the first things to do in Calc 1. How do you find that point algebraically? So, yeah, the one right here. In calculus, I like to talk about I'm skiing, right? So I'm skiing, go up the slope, and what are my skis right at this point? What slope are my skis at that point? Yep, at that high point, what is the slope of my skis? It's a horizontal fun